Today we're going to be looking at how to prove whether or not lines are parallel. So in the last few sections, what we've been talking about is that if we know that certain lines are parallel, so for instance L is parallel to M, then we can conclude things about certain angles. So we know things about angles. Like for instance, some are congruent, some are supplementary, and so on. So what we're going to be doing today is we're going to look at the converse of that. So today we'll be saying if we know things about angles, then we can say that lines are parallel. So we'll learn all kinds of tools in order to do that. And so it's going to look very familiar to you just because it is very similar to the sections before. It is simply the converse of those sections, the flip of those sections, if you will. So for instance, let's look at the first one, which is the converse of the corresponding angles theorem. So corresponding angles theorem said if lines are parallel, then we know that corresponding angles are congruent. So this is actually the reverse of that. So if corresponding angles are congruent, and I'm going to use a little bit of shorthand here, then we can say that lines are parallel. So for instance, let's use L and M. So then L is parallel to M. So for instance, specifically here, say that we know that this is, we'll say that this one is 110-ish. And we'll say that this one is also 110-ish. Well, those two angles are corresponding. So because they're corresponding, I know that because those are congruent and corresponding, I know that L has to be parallel to M by the converse of corresponding angles theorem. So you see how that works? It's basically the reverse of everything we did. Because those have the same measure, we know they're congruent, they're corresponding, so those lines have to be parallel. Just like we have a converse of corresponding, we also have a converse of same-side interior. So if a pair of same-side interior angles are congruent, not congruent, same-side interior angles are supplementary. Then I can say that L is parallel to M. So we'll call that L and M again. We'll call this one T. That's our transversal. So let's say, for instance, that this one is 60 and this one is 120. Well, because 60 plus 120 equals 180, and those are same-side interior angles, we know that L is parallel to M. So we are using what we know from last section to prove that lines are parallel, just the converse. We also have a converse of alternate interior angles. Says the same thing. If a pair of alternate interior angles, and I'm going to abbreviate a little bit, are congruent, then we know that L is parallel to M. So you need to be very careful when you're doing work, especially on a quiz and a test where all the sections are mixed together, that you know what you're trying to prove. Are we trying to prove things are parallel? Am I trying to prove things are congruent? Because the proofs are going to look different for each. So an example of alternate interior may be that this one's 60 and also this one's 60. So because those are 60, and their alternate interior, then we know that L is parallel to M. All right, moving on to the last one, which is converse of alternate exterior. Angles theorem. So if a pair of alternate exterior angles are congruent, I'm going to abbreviate, then we know that, again, those same two lines are parallel. So what we'll have to do sometimes is we'll be given a picture or a diagram, and we'll have to determine whether or not lines are parallel based on that information that we have. So alternate exterior may be like this one here, and then this one here. If I know that they have the same measure, then I know they're congruent. They are alternate exterior, therefore those lines are parallel. So let's look at an example of using this section and how we can use it in a problem, these converse theorems. So let's look at number 1. Which lines are parallel using the given information? Justify your answer. So for instance, let's look at part A. Part A says that 1 is congruent to 2. 1 is congruent to 2. So if we know that those two angles are congruent, what two lines can we determine are parallel? Well, 1 and 2 are what type of angles? They are corresponding angles. So let's see what lines they hit. They both hit transversal M, they both hit line A and line B. So what two lines would we be able to say are parallel from that information? Well, A and B. We can tell that M's not going to be parallel to either one of them. It doesn't even, it intersects it. So we know that A is parallel to B because the converse of corresponding angles theorem. And I'm going to abbreviate a little bit to save some room. So that's the converse of corresponding angles theorem told us that A is parallel to B. All right, let's look at the next little piece of information we have. 1 is congruent to 4. 1 is congruent to 4. Let's look at the lines that make up those angles. We have these lines here. So what lines could we say are parallel by those, knowing those two angles have the same measure? Well, we could say that L is parallel to M. Now, what type of angles are 1 and 4? 1 and 4 are alternate interior angles. So we can say that those two lines are parallel by the converse of the alternate interior angles theorem. You've got to make sure you use that word converse in your justification, because it's not the original theorem, it's the converse of that tells us those have to be parallel. Okay, let's look at the next one. 5 plus 6 equals 180. So again, let's look at the lines that intersect those. So what two can we say are parallel from knowing that 5 and 6 are supplementary? They add to 180 together. Well, we can say A is parallel to B. All right. Those are on the same side of transversal L, and they are interior. So we can say that by the converse of the same side interior angles theorem. And then the last one, part D. Whoops. Let's look at that one. So it says 3 is congruent to 5. 3 is congruent to 5. Well, those are vertical angles, right? 3 and 5. Let's see what lines they intersect. These two. Well, those two lines are definitely not parallel. So we actually can't determine anything from this one because we can't determine any lines are parallel. All the ones we have are A and L, which are obviously not parallel. So we can't determine that any are parallel based on that information, which you will have sometimes. All right, the next to last thing I want to look at with you guys is a proof of a theorem. We're going to go through this together. Now, you can see in the information that it says flow proof. If you want in class, I'll show you what a flow proof is. And if you prefer using a flow proof, you are more than welcome to. But I'm going to stick with our 2 column that we learned, just to stick with something you know. So what we want to do is we're given that angle 1 is congruent to angle 7. And I want to prove that L is congruent to M. So we are given 1 is congruent to 7. reason being given. And we want to eventually show that those lines are parallel. Now, we are trying to prove Theorem 3.7. Theorem 3.7 was the converse of alternate interiors theorem. So when you're trying to prove a theorem, you can't actually use that theorem in the proof. That is what we are trying to prove. That's the end goal. So we can't actually use it when we're proving this. So we've got to find some other way to do it. But let's see. If 1 is congruent to 7, what else is 1 congruent to? Well, we know that angle 1 is congruent to, the only other one I can say for sure would be 5. I could say 1 is congruent to 5. Well, we don't know the lines are parallel, so I actually can't say that. But I can say that 1 is congruent to 3, because they are vertical angles. I know that for sure. So 1 is congruent to angle 3. Whoops, that should be number 2. By the vertical angles theorem. Or you can say that vertical angles are congruent. You can actually write out the theorem. So I also know that 1 is congruent to 3. So if 1 is congruent to 7 and 1 is congruent to 3, then I also know that 7 is congruent to 3, right? And that's going to be by the transitive property. Or you can even say substitution property. And I would accept that. Okay, so I also know that 7 is congruent to 3. Now 7 and 3 are corresponding angles. And didn't we have a theorem that said if corresponding angles are congruent, then the lines are parallel? We did. It was the converse of corresponding angles theorem. So now I can go ahead and say that L is congruent to M by the converse of corresponding angles theorem. And that proof is done. Okay, so see how we're using other theorems from this section to help us prove things? So we'll be doing that a lot. All right, last thing I want to look at, and we are done. I'm going to find the value of W for which C would be parallel to D. So what value of W would make these two lines parallel to one another? I want to know how would they be parallel. Well, let's look at the two angles that we have. We have 55 here, and then we have this one. If C was parallel to D, what would be true about these two angles? Well, they're corresponding. So if those are congruent, then we know that C is parallel to D. So we need 55 to equal 3W minus 2. If those equal one another, then I know that those lines are parallel. So now we have an algebra equation which we can solve. So 3W equals 57. So W here equals 19. So when W is 19, C is parallel to D. At no other value of W are those two lines going to be parallel, only at W equals 19. So that is it for this section. Just know to prove lines are parallel, you need either that corresponding angles are congruent, same side interior are congruent, same side exterior are congruent, or same side interior are supplementary. And that's it. See you tomorrow.